Hello everyone. Uh, we'll just wait for some 5 more minutes. So anybody who wants to join, so they can join. Hello, hello. Am I audible, Mithran?
Yes, sir.
Am I audible?
Yes, sir.
Okay. So we'll start now. No one is joining. I think.
Yes, sir.
I'll share my slides. Is it visible, Mitran?
Yes, sir.
The slide is visible for you?
Visible, sir.
Okay. Okay. So, good afternoon, everyone. My name is Ankur Khapre. I am from University of Hyderabad. I am doing this teaching assistantship for this course that is uh, depicting as a introduction to crystal elasticity and crystal plasticity. The course instructor is Professor Swarup Gaur from IIT Guwahati. So I'll just start from my question number one. So question number one is the close packed direction of BCC crystal is. So here we have to understand what is the BCC crystal first. So I'm drawing here BCC crystal. How it will look like. In BCC crystal, there eight crystal lattice point will be at the corners and one will be in the center of the uh, cubic. Okay, so the question is the direction of the close peg direction of the BCC crystal. For that, here the written is here the direction with high linear density is the close peg direction. So what is the close peg direction? The direction with high linear density, that is called close peg direction. So here you can see the linear density. I'll just remove this part. Okay. So here you can see the linear density. Linear density is equal to what? The number of atom in the direction of the vector and the length of the direction vector. That is called linear density. So in BCC crystal, what will be there? First, we'll check about FCC crystal for the like um, for understanding. So I will write here this crystal FCC lattice. So each and every corner there will be one lattice point. So total 8 will be here, and other will be in the middle of this face face of each plane. So you can understand here, says linear density. First we'll check in this direction, okay, from here to here, this direction. So for that, here how many atoms are coming in this linearly? This wait, I'll just change color. Okay, this atom is coming and this atom is coming. So here we are saying that two number of atoms are in the direction of the vector, in this vector. Okay, so I'll just write a two number of atoms in the direction of vector. And what about length of the direction vector? So here we are seeing that this length is around, since this length we are taking a, so it will be calculated by Pythagoras theorem. So it will be around root 2a. So we can understand here that in this direction the linear density is around 2 by root 2a. And what about this direction, the straight, like this x-axis? I'll just consider the x-axis. This will be y-axis, and this will be z-axis. So here only one atom is there in this x-axis direction. So we'll consider some another color. I'll take, okay, this atom. So here only one atom is there. So for this direction, x direction, linear density will be around approximately one, not approximately, sorry, it will be like one atom, and the length of the direction vector is how much? A. So you can understand here, this length and this length, if we'll compare, then which will be bigger? Obviously this one. So linear density will be higher in this plane, this vector direction. So for better understanding, we have taken this example. Now we'll just start for our BCC crystal. Here you can see the linear densities. First I'll try, first I'll draw. So here I'm considering a BCC crystal lattice. If we'll go from this direction to this direction, so how many atoms are there? Only one atom is there. So we'll just write a number of atoms in the direction of vector is 1, and the distance, this length, sorry, The length of the direction vector is around root 2a. What about this direction? Sorry. What about this direction? Again, it is around same root 2a. And what about this direction then? Sorry, here one atom is there. So this direction. So it is a 1 1 1 direction. So just I'll write how many atoms are there. So two atoms are there in this vector direction, and the distance is around root 3a. So according to this, the linear density will be higher in this side. So if we'll go this side, either this side or that side, there is no change in the linear density. It will be remain same, but in this direction, diagonally, it is changing. So changing means a higher linear density is there. So um the answer will be, since it is starting from this, the origin is this one. So we'll consider this point as a one, this vector direction as a 1 1 1, and that's why it is, the answer is this one. Okay. Hello, Mitran. Somebody there? Are you under? Can you understand this, Mitran? Okay. Now we'll move toward the next question. So before that, I will just discuss about another one, SCC crystal lattice, simple crystal, cubic crystal lattice.
Excuse me, sir.
Yeah, are you understand? This is
Uh,
understandable for you?
sl- yes, sir.
Okay. Now I'll continue for this.
Slide is not, sir. Sir, slide is not show in screen, sir.
It is not visible for you, the slide.
Yes, sir. Yes, sir.
Okay. Now, is it visible?
No, sir. Yes, sir.
Before it was visible or not?
Yes, sir. Visible, sir.
Before, previously it was visible?
Yes, sir. Visible, sir.
Okay. So now I'll, okay. Please mute, Mitran. Okay. So now I'll discuss about the one acidic crystal lattice. here you can see there is no atom in the middle of the cubic lattice, and also as well at the faces, only on the corners of this lattice. So here if you'll go in this direction also, this direction as well, and this direction, only one atom is in the that particular direction, particular vector direction, and the length of the direction vector is around, here it is a, this one y-axis, also just write LD for y also, for x also, and for z also. It will be 1 by a. What about this one? It will be one atom is there, and the, sorry, it will be LD. So in this direction there will be one atom will be here. So LD 110 equal to only one atom, and the length will be root 2 a, since this length is around a. So this is according to Pythagoras. We can calculate through Pythagoras theorem. So it will be root 2a. Okay. Now we'll move further toward next question. Here the question is stacking arrangement of FCC crystal is. So here are three kinds of. I'll discuss one by one FCC also, HCP and CCP, how they are arranged, stacking according to stacking. So first one is HCP. I will discuss, since it is a hexagonal packing. Here hexagonal packing. So the atom will be present in this corners and middle of the space. Here also same, but the middle atom will be different, since there will be some void. So this atom will be like this, three atom will be there in uh, two packings, two layers. So here you can see this one is around, this one we can say A, and this one will be B, and another it is again repeating A, stacking. So for HCP it will be A, B, A, B, A manners. Okay. What about CCP? CCP will be same, very little difference is there. Here another layer will be there. This, and just erase this, then it will be visible properly. First three atom will be like this, and another three atom will be like this. Okay, so here the packing will be like B, and this one will be C. So in CCP, packing will be A B C, A B C. Sorry, A B C. Okay, A B C, A B C. Now we'll move to our question. So they are asking the stacking arrangement of crystal FCC crystal lattice. So for that I'll draw the FCC crystal lattice. So now uh, here I'll show how it is, okay, how it is arranged. I'll show with different color, then it will be understandable for everybody. Okay, I'm showing this first atom of this corner with sand color. Then I'll use red color or some other lattice point. Okay, so this will be in this in this fashion. Okay, and then another color, green color. This is the another lattice layer, and in the last, again the sand color will repeat. So how what you are understanding here? Here in FCC crystal, three layers are here. First one is A layer, second one is B layer, third one is C layer, and the last one again it is repeating as a A. So in FCC, the stacking arrangement is A, B, C, A, B, C manners. So the answer will be A. Now we'll move forward to the next question. Here, the question is sufficient ductility is observed in which of the following type of atomic bond? So there are different types of bonds are there mentioned in options. First one is metallic bond, second one is covalent bond, third one is ionic bond, and fourth one is Wonder Walls bond. So we already know that metals are like little. We can see in our daily life that metals having some ductility compared to some plastic or something else. More ductility will be in the metals. So here metals are having so many delocalized electrons on the surface of metals. So due to the this delocalized electrons, see the metallic bond between atoms can easily broke and reform. So as we also know that gold wires we can ductile and ductility is too much and we can make a wire so much thin wire from platinum and silver copper metals also we can use. So here the option will be straightforward the metallic bond. Why not covalent bond? Covalent bond is having some restriction with some angstrom level. We have that force between the two atoms will be too much compared to this metallic bonds, and if it will break, then the for bond breaking itself it is taking so much energy, and the formation is not possible. So covalent bond is, we can't say the ductility is there. Ionic bond, yeah, ionic crystals all are brittle, so we can't say that also. And sufficient like compared to metallic bonds I'm telling. And in van der Waals bond also, it is like some polymers and crystals are having this van der Waals interaction, like pi interaction and at ch pi and chn interactions. So it is possible, ductility is possible but not that much. So the answer will be metallic bond. So we'll move toward the next question. Here the crystal system of gypsum is like, it is a calcium ore. So it is having a crystal system of like orthorhombic manners crystal system. So what is the Miller indices of the plane whose intercepts are at a by 2, b and 2c in the simple cubic unit cell? Here we'll I'll just write down. I'll just make a figure for simple cubic unit cell. Okay. Now I'll just write the intercepts where it will form, where it will intercept the axis. Okay. So first I'll write this axis first, y-axis. This one I'm considering as a x-axis, and this one I'm considering as a z-axis. Here, this intercepts are a by 2, b, and 2c. Here, we'll just take a reciprocal of this intercepts. So we'll just forget about this values a, b, c. 1 by 2, 1, and numerical value will take for reciprocal. So for this, the reciprocal will be 2, for this 1, and for this 1 by 2. Now we'll multiply the denominator with the numerator. So it is our Miller indices for A2, B, and 2C. So I'll just write down how it will look like. So here we are considering this part as the origin, and this in x-axis it is intersecting at a by 2. So here will this point will consider for this a by 2, and for b it is intersecting here at y-axis at b, and for c and for g-axis it is intersecting at 2c. So this length is c, so now it is coming double of this c, so here somewhere it will come. So I'll just make a plane for this particular Miller indices. So this is our plane. Okay. So the answer will be what we have already did. Once again I'll write a by 2, intersect I'll write a by 2, b 2c, and we'll just take numerical values, and since it is a cubic unit cell, so a, b, c will be equal. That's why I'm taking only numerical values. Now I'm taking reciprocal of this. Now multiplying the denominator with numerator. Okay, so our Miller indices is 4 to 1. So answer will be first one. Okay, so we'll move next toward the next question. Here, okay, so here the Miller indices of the corresponding direction OA, OC, OD, and OF from figure given below we have to identify. So for that, first we'll consider this OA direction. So OA direction you can see here OA. So this direction we are considering first OA. Here this A point is intersecting at x-axis. So intersecting points will be 1, infinite for y-axis, and infinite for z-axis as well. Now I'll take reciprocal of this intersects 1, 0, 0. Since the HKL value should be integer and these values are integers, so we'll consider these values as a Miller indices. So for OA direction, the Miller indices will be 1, 0, 0. So only one option is there, but we'll solve for another directions as well. So we'll solve for OC direction now. Here you can see the C is at a intersecting point for C is 1 from at x-axis, 1 at y-axis, and 1 at z-axis. So taking a reciprocal as well also, the value will be same. So the Miller indices will be 1, 1, 1. Here also you can see this OC direction, the Miller indices will be 1, 1, 1. So our option is matching. Now we'll calculate for this too. So first, what is there? OD. So OD direction is this one. So where it is intersecting? At x-axis, it is intersecting as a 1. In z y-axis, it is not intersecting. So infinite. in z axis it is intersecting at a 1.5. So now we'll take a reciprocal 1, 0, 2. Now we don't have to divide to anything because it is an integer itself. So this value is Miller indices for OD. I'm sorry for that. Something wrong is here. Okay, I'll just calculate again. I did mistake here somewhere. Okay, for OD, we'll consider one. It is intersecting at x-axis. Y it is not intersecting, so infinite will take. And Z it is intersecting at half of the axis. So now we'll just take reciprocal 1, 0, 2. Hence the answer will be this. I think this written is wrong. I'll just check and correct this. And for we'll move toward the OF direction. So for OF direction, we'll calculate the corresponding Miller indices. So it is in y-axis. It is x-axis. It is at 1.5 and half, and at half. And for y-axis, it is also half. At z-axis, it is at 1. So if we'll take the reciprocal, so it will come 2 to 1. Okay, so answer will be this one. I think their mistakes are there. I have to correct. I have to check again. Okay, we'll move toward the next question. Here we have to calculate the angle between 111 and 11 prime 2, direction of negative 2 directions in cubic unit cell. So first uh, we'll see what is the formula for this. Before that, we have to know how to calculate this uh, angle through this direction vectors. So since directions are vectors, we can use vector to find the angle between them. So here I am taking this. It's given there 1 1 1 and 1 1 negative 2 minus 2. So here two vectors are there. Now we have to calculate the angle. So the formula is cos alpha is equal to a dot b by a mod a dot mod b. So that's how we can calculate, or this alpha, for alpha we can calculate like cos inverse also we can do this side like this. So here we have to calculate for cubic unit cell and the direction is given. So I'll take this here. The angle will we have to calculate is this one, alpha. So for alpha calculation we have to do cos inverse, we have to calculate this values a dot b upon mod a dot mod b. So we know a dot b is what, dot product. So dot product is, we can write like this, cos inverse 1 I dot I, so 1 into 1, then plus j into j, so 1 into 1, and k, this 2k values is like 1 and minus 2, so 1 into minus 2. Then we have to divide to the value which is mod a. Mod a is like I, corresponding to I value, it is like 1, it is here 1, another value is 1 again, so 1 square, and in k also the value is 1, and another root inside that 1 square, it is corresponding to I value, and another 1 square, that is from j value, and here minus 2 square. So the value will be 1 1 and minus 2. So the numerator is 0, denominator is root 3 and 0. So here the value is 0. So cos inverse 0 is equal to, we have to calculate. So alpha is equal to cos inverse 0. So alpha is equal to 90 degree. Okay. So the answer will be 90 degree. Now we'll move toward the next question. Here we have to calculate the planar density. So the question is, an FCC structure has a lattice parameter of 0.396 nanometer. Determine the planar density for the 111 plane of FCC structure. So what is given here? So lattice parameter is given. This value is given already, A, and For planar density, we can go through this formula, so we can calculate the planar density. So number of atoms on a plane and number of planes, area of plane. So that for that thing, first we have to find out what is the 111 plane. So find the number of atoms in 111 plane. So this is a FCC structure. In that, this is the 111 plane. On that, you can see the number of atoms. There are three atoms are at corners. So the contribution of the corner atoms is 1 by 6. These three. So here the contribution 1 by 6 into 3, and the spaces atoms contribution is 1 by 2. So 3 atoms are there. So total number of atoms on this plane is 1 by 2 plus 3 by 2, which is equal to 2. Now we have to find the area also. For area, since it is a triangular, we know that this value is already given, lattice parameter, that is 0.396, and this value we can calculate through Pythagoras theorem. So here the value is a. Now it became root 2a according to Pythagoras theorem, and this value we have to find out because we have to find out the area of plane. Okay, so this value is root a by 2, so we divided by root by 2. Now this value will be whole square root 2a whole square minus a by root 2 whole square is equal to h, this height. Okay, so now it is coming around root 3 by root 2 a square, sorry, a. Now this is h value. Now we have to calculate the area. For that, this value and this value, we have to, area of triangle is 1 by 2 root 2a, since this value is root 2a, and height, this is base and this is height. So height is root 3 by root 2a. So this root 2 and this root 2 got cancelled. Now it became root 3 by 2a square. And since this value is given in nanometer, so we have to uh, calculate the value in centimeter because the options are in centimeter. So what we'll do, root 3 by 2, 0.396 square into, sorry, into 10 to the power minus 18 centimeter. So this area will be this much. And now we have to calculate the planar density. For that, we'll just keep first number of atoms on a plane is 2, then root 3 by 2 into 0.396 whole square into 10 to the power 18 minus 18. So it will be points or atoms, whatever we can consider, per centimeter square. Now, after calculation, after calculation, we'll get this value. Since this 10 to the power minus 18 is downside, so we'll take it up 10 to the power 18 and we'll just remove this part. After calculation, we'll get this value. Okay. Now we'll move toward the next question. Question is, ANM has HCP crystal structure with atomic radius of 0.173 137 nanometer and C by A ratio is as 1.615. Compute the volume of the unit cell for rhenium. So here, since this is HCP crystal, so I'll first make a HCP crystal lattice. Crystal cell. Okay. Hmm. So here we'll divide this portion into six parts. Okay. So and here the return is that C is this length, HCP cell length, height, and A is the distance between two atoms. Just two. And it's given that radius R is 0.3137. So first we have to find out A. So how we can find out? So A is around 2R in HCP. So it will be double of this value. After that, we have to find out C value, since C by A is equal to 1.615. Okay, so A value we know already, so C will be 1.615 into A, and we have to calculate the unit cell volume. So volume will be, here will consider first this as a point, this as a B point, and this origin, this center as a C point. So the area of this will be one sixth of this area of the plane, this the bottom plane. So we'll consider 6 times area of the angle, area of this triangle A B C, and the height of the HCP cell, unit cell. So height is C. This C and this C, make sure that this is different. So A, again the volume will be A, sorry, 6, and the angle, this sorry, this triangle, the volume is, so area will be, since this value is A, this also will be A, and this also will be A. So the middle value will be, we can calculate again through Pythagoras theorem. Okay, a square minus a square by 4 whole root. So it will be root 3 a by 4. Okay, so this value will keep here into C. C is all C we can calculate from here. Sorry, here A I missed. A and the C value is around 1.615A. Now I'll just erase this part. Okay, so the volume of the unit cell will be 6 into root 3 by 4 into 1.615. 2 times a are there, so a square. So a square is equal to 2, sorry, a is equal to 2r. So we'll keep a square as a 4 r square. So r square is value is 0.137 nanometer. Nanometer square. If we'll calculate the value, so we'll get the final answer, option A. Okay. Hello, Mitran. Yeah,
Yes, sir.
is it understandable for you till now?
Yes, sir. Yes, sir.
Yeah, is it understandable?
Yes, sir.
Okay, I'll continue further. Few more questions.
Yes, sir.
Okay, so now we are going further toward the question number 10. Find the interplanar spacing for a one-to-one plane in a simple cubic lattice whose lattice constant is 0.412 nanometer. Okay, so what is given here is lattice constant, that is around 0.412 nanometer. It means like lattice constant is a value, and it is given here. And another thing is given here is interplanar spacing. Plane is given here, 1 to 1 plane. So, and the main important thing is simple cubic lattice is given. So first I'll draw the simple cubic lattice here. I'm so sorry for my drawing. I'm not used to with this, mm, this pad, writing pad. Okay. Okay. So now, uh, as you can see here, I drawn the simple cubic lattice. In that, I have to see where is this plane. For that, we can either we can take a reciprocal and we can go for the intercept. That will be good. So first, what I'll do is it is a simple cubic lattice. So first I will do take a reciprocal for this. Okay, one by one, one by two, and one by one. So what is their um, intercept? Intercepts are 1, 1 by 2, and 1. So in x-axis, it is intercepting as at 1. In y-axis, it is at half, and in z-axis, it is at 1. So the plane will be this one. Okay, this plane. So for this plane, we have to take a we have to calculate the interplanar spacing. So interplanar spacing is just normally called d, and we'll just write here HKL value. Okay, normally. So for and the formula is for simple cubic formula will be A by under root h square plus k square plus L square. Since the lattice constant value is 0.412, so I will write here 0.412 divide by HKL values are there 1 square, 2 square, and 1 square. So the value will be 0.412 upon this will be 1, this will be 4, and this will be 1. So 6. So root 6. Okay. Okay, let's series this. 0.416, oh, sorry, 412 by root 6. So the value will be, okay. So the value will be approximately this. After calculation, it will come like 0.16 nanometer. So the interplanar distance will be, spacing will be uh, 0.16 nanometer. So now the next question. So how many atoms per square millimeter are there on 10010 plane of lead? Assume the interatomic distance to be 3.499 into 10 to the power minus 10 meter. Okay. So here one trick is there. First you have to see whether this values are matching or not. First check in options. In question the value is given in meter, and the options, it is written in millimeter square. Okay, so first we have to see what is the uh, crystal structure. So cell will be for lead, is BCC. Okay, you have to find out this by your own self. After that, sorry, it will be simple cubic. I'll just write down. Okay, so simple cubic, lead will be simple cubic, and then after that, here we have to assign the plane first. For that, we have given Miller indices 0, 1, 0. So the plane will be at x-axis it will be 0, at y-axis it will be 1, and at z-axis it will be again 0. So the plane will be this plane. Okay. Here how many atoms are there? 4 atoms. Now they asked how many atoms per square millimeter are there on 0, 1, 0 plane of lead. Assume the interatomic distance is this much. So interatomic distance in the sense this value, A value. Okay. So the formula for the this is again the example of planar density. How many atoms per square millimeter means it is asking for density only. So it is a planar density. Planar density for this will be number of atoms upon number of atoms in on the plane upon area of the plane. Okay. So for that, first we'll calculate the number of atoms on the plane. Here you can see 4 atoms are here, but the contribution will be there. So the contribution will be 1 by 4 for each atom. Okay, atom contribution. So the total number of atoms will be on this plane will be 1 by 4 into 4. Since each is having 1 by 4 contribution, and total number of atoms are 4, so the total number of atoms will be 1 on this particular plane, and the area of the plane we can find out using this atomic distance a. For that, sorry, planar density. Okay. For that, the area is a square because it is a SCC lattice. So area is equal to a square, and a square is what? 3.9, sorry, 3.9499 into 10 to the power minus 10 whole square meter square. But okay, I'll just erase this part. So, but the here they asked in square. So either we can change this value after this putting in this planar density formula or before itself. So I am considering here before putting we can change the value to square. So the our area in square will be 3.9, sorry, 3.499 into 10 to the power minus 10 whole square into 10 to the power how much? Meters, so millimeter 10 to the power 6, so 10 to the power 12 m millimeter square. So now we'll put in this uh, main formula all the values. So number of atom how much calculated? 1. And the density is this much, 3.499 square into 10 to the power minus 8 m square, and this value will go up, so it will become 10 to the power 8. Okay. Now the planar density will be atoms. How many atoms are there? 1. And the value is sorry, 10 to the power 8, 3.499 to the power 2 atoms atoms per square. After calculating this, we'll get the value option 2. Okay. So how that's how we have to calculate the planar density. Previously also we have calculated in points and atoms. Don't confuse with that. We can consider atoms, molecules, or points for this lattice. Now the next question. Here the question is little bit uh, simple, but as well tricky. So how we can calculate the density theoretically? We have to see. For theoretical calculation, we have to theoretical calculation. Density will be, sorry, number of atoms, and A, molecular weight, atomic weight, and volume, and Avogadro number. So this is the theoretical calculation of how we can calculate the theoretical density. Theoretical calculation of density. So if we'll keep each and everything, so we can get. So for that we have to we need to know that molybdenum, what is which kind of cell, cubic cell is this. So this is a BCC kind of cubic cell. Molybdenum contains BCC kind of cubic cell. For that, n value is 2. Okay, and A value is given. A value is given 95.94 gram per mole. Okay, mole inverse. And Avogadro number we know already, 6.023 into 10 to the power minus 23, sorry, plus 23. Okay, now density is also given here. The molybdenum has a density of this much, and we have to calculate the radius. So first I'll write density, how much is given, 10 to the power 2, sorry, 10.2 into 10 to the power 3 kilogram per meter cube. Now I'll just modify this formula. Okay, I'll modify with this formula, like volume we know what is that, AQ, the uh, length, length cube. So for BCC, A is around root 3 is around 4A. Root 3A is around 4R, sorry, 4R. And so we can write A as this one, 4R by root 3. And this A we can write here volume. Volume is around, now volume will become 4 by root 3 whole cube. And we know that volume is what? Now uh, volume is n upon n into A. N is a n value, atom number of atoms. A is atomic weight, and we'll just change the row shift here and Na. So here if we'll keep this value here and these things, so what we'll get? So volume equal to 2 into sorry, first I will change, first I will convert this one as a R. So what we'll get in the end? R is equal to 2 into A is what? A value is 90.95.94, then into 3 to the power 3 divided by 4 to the power 3 into row values 10.2 into 10 to the power 3, and Avogadro number 6.023 into 10 to the power 23. This will come in, sorry, here one thing I forgot. It is in, this density is in kilogram, so we have to convert it in a gram. For that we have to just multiply with 10 to the power 3, so it came converted into gram. So now it will come in meter. The value will come in meter, since, oh, one thing also, this, sorry, this whole value, it its power will be 1 by 3, so it will come into meter. Now we have to convert into angstrom. For that we have to multiply the whole value with 10 to the power 10, so we'll get the value in angstrom. Okay, so the our answer will be, so our answer will be option number A. After calculation it will come 1.36 angstrom. Now we'll move toward the next question. uh, so question is, what are the Miller indices of the plane in blue shade given in figure below? So you can see here what they have mentioned. It is a very simple question, but the picture diagram is not visible properly. So this is A1, this is A3, I will just tell you orally, and I'll just write this. This is A2 and this is Z. Now, normally how we are calculating this Miller indices? We are calculating in HKL manner. Okay. Here the things are different. We have to calculate HKIL for values of Miller indices. For that, first we'll start from here. Wherever it will intersect or it will intersect, we have to see and we have to uh, give the value of the Miller indices. So as you can see here, at point A, at point A, the starting from here to here, and this it is intersecting at point A, this this place. So according to that, we can say it is in positive and 1. Sorry, no comma. Then see in the A2, A2 you can see it is not intersecting at any point, so we can consider it as a 0. Now if we'll move further toward the A3, here you can see it is not at all intersecting, but it is intersecting at the negative side. Okay, so in the negative side, if it is intersecting for A2, A3, so we'll write -1 or 1 bar also we can write. So both things we can show 1 bar, and here you can see it is intersecting at G uh, at G also, so we can write 1 intersecting here. Okay, so the right answer will be the last one, 1 sorry, 0, 1, -1 and 1. Okay, now the question number 40 here, what is the theoretical density and linear density along 110 of chromium? Assume atomic weight of chromium to be 52 gram per mole and atomic radius is 0.125 nanometer. Okay, so first theoretical density we already saw on this formula. Sorry, rho is equal to n a upon v uh, na. So according to that, what we can do, just we have to write for chromium. This is a BCC lattice. Okay, so for BCC lattice it will be 2, and will be 2, and A will be what? A will be given here atomic weight, that is 52 gram per mole, and what else is given? Radius is given. So radius we can convert into volume. How we can convert? We know that for BCC we have already shown that 4r upon root 3 whole cube. So from this we can convert this r value here. We can write, so the r value will be, oh sorry, so the v will convert to this one. So we'll write here r form. Okay, and here the Avogadro number will be same. So Na And if we'll calculate these values, then we'll get the 7.18 gram per centimeter cube. For that, one thing is there, this nanometer cube we have to change into centimeter cube. For that, we have to multiply with 10 to the power 21 minus 21. Okay, so it will become in centimeter. Okay, so that's how we have to calculate this row value. And the linear density, for linear density we know already, in this plane, particular plane, we have to draw this plane first. BCC. So plane, it is plane 110. So 1 1, sorry, 2 1 1 0. So this plane. So here total atoms will be, okay. It is not a plane, sorry. It is a vector. So this vector they are asking. Okay, 1 1 0. So this vector, here only one atom is there. So number of atom will be 1 for particular this atom. And the area will be, since the A is around, sorry, the vector is around root 2a, so it will be root 2a. And if we'll keep this values, a will be here, root 3, sorry, sorry, 4r by root 3. Okay, if we'll keep in this formula, we'll get the value of 11.28. Okay, now here the last question, calculate the theoretical volume change in percentage accompanying a polymorphic transformation in a pure metal form. The BCC to FCC to BCC crystal structure. Assume the hard sphere atomic model and that there is no change in atomic volume before and after the transformation. So first, percentage change we have to check. For that, percentage change after the, sorry, percentage change while converting FCC to BCC. Okay, so for that, how we can calculate? First, we have to calculate the volume of BCC, volume of sorry, here FCC, volume of BCC upon volume of FCC. So we know FCC volume what will be there, 0.74 minus 0.68 for BCC, and the volume of per unit cell will be uh, 0.74 for FCC again, and that's how we can calculate the value approximately around 8.8%. We have to multiply with 100 so we can get whatever we are value we are getting from here, 0.06 upon 0.74. So in the last we'll get the value 8.8 percentage. Now I'll wind up this here. So Mitran, did you understood today's questions answer? Can you calculate now?
Yes, sir.
Is it a, is it okay? Can
Yes,
you
sir. I will
calculate,
understand, sir.
like now you can understand whatever I told you, this question
Is it
solution?
okay, sir? Is it okay, sir?
Okay. So I'll wind up here. Thank you for joining this session.
Yes, sir.
Okay.
Okay, sir. Thank you for your valuable question, sir.
Okay. Thank you so much.
Thank you, sir.
If you have some doubt, you can ask.